In the past few lectures, we've learned a lot about alkanes. We've looked at their structure, we've looked at how to name them, and we've also looked at different ways of drawing those alkanes. Now, of course, the question we should always ask ourselves is, why do we care? What do alkanes do for us? Where do we see alkanes, and how do we use alkanes in our everyday life? Now, as you'll see here, we have an alkane represented in our skeletal structure format. We have 8 carbons, one at each of the vertices of our line, and so this is octane. Octane is one of the alkanes that we see commonly around us. Octane is a major component in gasoline. So of course you might recognize octane. We talk about how much octane content gasoline has, which is basically an indicator of how powerful that gasoline will be. So gasoline, of course, is very useful to us. It has several key properties that we see as we use our gasoline. The first and most important property, of course, is that it is combustible. Right? We burn our gasoline in order to power our combustion engines in our vehicles. However, it also has several other key properties that you've probably noticed. So it's very volatile. That means that it can easily evaporate into the gaseous state. So that's why there are strong gas fumes whenever you're working with gasoline. Right? So it forms gas vapor, and then you smell that. It also is water insoluble. Right? So you've probably heard gasoline and water don't mix, or oil and water don't mix. Oils are often relatively similar to alkanes or composed of alkanes. So these are 3 of our key properties for gasoline, which is composed primarily of alkanes. And these 3 key features also are true for other alkanes as well. So we're going to take a closer look at the structure of alkanes in order to see why we have these 3 key features, and then we'll also look at how they vary between different alkanes. So let's start out by looking at the intermolecular interactions of our alkanes. And these intermolecular interactions will be key for determining how volatile a compound is, and also how soluble it is in water. So going back to general chemistry, of course, our 4 key intermolecular interactions are London dispersion forces, also called van der Waals interactions. These are those temporary dipoles that are created by the random motion of our electrons. We have permanent dipole-dipole interactions. So these occur when we have polar bonds in our molecule that then create those partial negative and positive charges that can then be attracted to other dipoles on other molecules. We have hydrogen bonding, which occurs between the strong dipoles that we have associated with hydrogens attached to electronegative oxygens or nitrogens and other electronegative atoms. And of course we have ionic interactions, which occur between positive and negative charges. For these intermolecular interactions, of course, our strongest are ionic interactions and hydrogen bonding. Our weakest are London dispersion interactions. In all of our alkanes, such as our octane right here, so remember, of course, we have our carbons at each of the vertices of our skeletal structure, and of course they also have hydrogens bonded. I'm not going to draw in all of the hydrogens, but I'll just show a few of the hydrogens here at the left side. Now remember, our hydrogens and carbons have almost the same electronegativity, so these are essentially purely covalent bonds with no bond dipoles. Now as soon as you hear that we have no bond dipoles, we can immediately eliminate dipole-dipole interactions. We can eliminate hydrogen bonding, and of course we can tell there's no charge here as well, so we can eliminate ionic interactions. So that means that our alkanes only have the weakest of our intermolecular interactions which is our London dispersion interactions. Anytime you have weak interactions, that means that you are going to have lower melting points and lower boiling points, and you'll have a more volatile compound. Right? So those interactions tell you how strongly your molecules are going to be held together. If your molecules are held together very strongly, then you're more likely to have a solid. Right? A solid state, you have all your molecules packed tightly together, where they can get lots of interactions between each other. When they pull apart more into the liquid state, you have to break some of those intermolecular interactions. And when you move from the liquid to the gas state, you break almost all of your intermolecular interactions and just have your molecules floating around almost completely independently. So since this is a weak interaction, that means that our molecules are going to be easier to pull apart from each other, and so we'll have lower melting and boiling points. And again, of course, this is what we see for gasoline. Gasoline is very volatile. You can easily produce those gas fumes, which creates, of course, that characteristic gasoline smell, as well as, of course, the danger that can be associated with those gas fumes as well. Now, of course, that tells us why gasoline and octane are volatile. The next question we want to ask is, how does that vary between different alkanes? To answer that question, I want to compare two different alkanes. We have butane over here on the left, and of course our octane over here on the right. Now I have two molecules of each shown. Each of these molecules, of course, can interact with each other through our London dispersion intermolecular interactions. So I'm showing my arrows here representing the attraction that occurs between the temporary dipoles of my carbon and hydrogen atoms on one butane molecule and my carbon and hydrogen atoms on the other butane molecule. I, of course, also have those same London dispersion interactions over here on my octane. And now if we compare our two molecules, our two alkanes, notice we have a few atoms here interacting. I have my 4 pink arrows representing the interactions between my 4 carbon atoms. Over here I have my 8 pink arrows between my 2 octane molecules. And what that shows is that we have a lot more interactions here just because we have a lot more carbon atoms and hydrogen atoms that can interact with each other through those temporary dipoles of our London dispersion interactions. More interactions equals a stronger interaction overall between our two molecules. So we have a stronger attraction between our octane molecules than we do for our butane molecules. And of course, a stronger interaction leads to a higher melting point and boiling point. I'm just abbreviating here our melting point and boiling point for our octane. So while we concluded before that octane has a relatively low melting point and boiling point, butane is actually going to have an even lower melting point and boiling point. As it gets smaller, it has less interactions that can occur between those molecules, and therefore it's easier to pull those molecules apart into the liquid or the gaseous state. So we can conclude then that for all of our alkanes, higher molecular weights, so larger alkanes, will lead to higher melting points and boiling points. So that's our first key conclusion. When we look at different alkanes, the size of our alkane is going to relate to the strength of our interactions and our melting point and our boiling point. Next, let's compare a linear alkane, our butane here, with a branched alkane. Now notice both of these alkanes have 4 carbons. Can mark them out at the vertices of our skeletal structures. Each of these carbons would have hydrogens attached up to their 4 bonds per carbon. And so they actually both have the same molecular formula, C4H10. Now, since they have the same formula, but our structures, of course, are obviously different, that means that they are structural or constitutional isomers. So their molecular weights are the same, and we can't conclude from our previous statement which one would have the higher melting point or boiling point. But if we compare our molecules again and look at the London dispersion interactions, we can see as we place our molecules next to each other, so we can have our interactions all along the chain of our butane, whereas here our molecules are a lot harder to pack together and get as many interactions with our branched 2-methylpropane molecule here. So our branched molecule is harder to pack together, and then that means that it's harder to get as many London dispersion interactions between our atoms here. Alright, so we can kind of poke one of our branches toward it and get some interactions, but it's harder to have all of our atoms lined up next to each other like we have with our linear butane. So now our butane is going to have the stronger interactions, and our 2-methylpropane here will have the weaker interactions, which again will translate to our melting point and boiling point. Weaker interactions leads to lower melting point and boiling point. So we can make another conclusion here. We say that more branches leads to a lower melting point and boiling point. Those branches interfere with our interactions. It's harder to pack our molecules together to maximize the interactions. We don't have as much surface area, essentially, between our molecules. And so that reduces the interaction, makes it easier to pull those molecules apart and make our more volatile alkane. Our next key feature for our alkanes also relates to our intermolecular interactions. So this is our water solubility. So as we said, our alkanes have London dispersion or van der Waals interactions between our carbon and hydrogen atoms, whereas water of course has our H2O, our oxygen with its lone pairs and high electronegativity, means that we pull electron density towards our oxygen and create strong bond dipoles within our oxygen molecule. This, of course, leads to hydrogen bonding, and dipole-dipole interactions between water molecules. Now, one of our key rules whenever we look at solubility is that we want like to dissolve like, right? So molecules want to hang out with other similar molecules because it can have the same interactions with those molecules that it can have with other molecules of itself. When our water mixes with alkanes, so here's our butane and our water molecule. So the water molecule wants to do hydrogen bonding, whereas our alkane wants to do London dispersion interactions. So the water molecule would much rather make its strong hydrogen bonds with other water molecules and leave our alkane out of it. Right? It doesn't want to form weak interactions with our alkane when it could form those strong hydrogen bonds between our other water molecules. And this is what leads to that water insolubility. The larger our alkane is, the harder it is for it to mix with water, the worse it is, because the more it breaks up our hydrogen bonding of the water. And so our higher molecular weight of our larger alkanes leads to a more insoluble molecule. So our octane of our gasoline, it's very water soluble, or water insoluble, because it has a higher molecular weight, it only has those London dispersion interactions, it can't hydrogen bond with our water molecules. The last key feature of our alkanes is the combustibility. Now combustion, of course, is a reaction, so we will also refer to this as the reactivity of our alkanes. Now for our alkanes, really combustion is the only reaction that we commonly see. So we put that as our main reaction here under our reactivity. Now of course this is because our molecule doesn't have very many differences in electron density, right? So we have these essentially purely covalent bonds. We have roughly the same electron density across our molecule. If you remember from our look at acid reactivity, it's areas of high and low electron density that tend to make more reactive molecules. So our alkanes tend to be not very reactive in general. They just react in combustion reactions primarily. So combustion, of course, as we know from general chemistry, is the reaction of our carbon molecule with oxygen. So oxygen is our key factor for combustion. Of course, we can suffocate a fire just by removing our oxygen, because that's required for a reaction here. And that produces water and carbon dioxide. So this is an oxidation reaction. Our carbon actually gets oxidized to form our carbon dioxide in this case. Now, of course, this is our unbalanced chemical equation. We can balance it just by adding our stoichiometric coefficients to have the correct numbers of atoms on either side. I would put a 2 here and 25 here. And I'm going to produce 18 water molecules and 16 carbon dioxide molecules. This equation would be the same for any of our alkanes. We would just have to change our stoichiometric coefficients based on the number of carbons in our alkane that's being combusted. So all of our alkanes will undergo similar combustion reactions. We'll just have differences in how much oxygen is used or how much carbon dioxide is produced. The other difference will be in the heat of combustion. Right, so this is, of course, an exothermic reaction. So we can think of it as producing heat, represented with my delta H over here, my enthalpy. So this is my heat of combustion. And the heat of combustion will vary for different alkanes. Right? So all alkanes will undergo the same combustion reaction, will just vary in how many molecules react and how much heat is produced. As you might expect, the larger a molecule is, the more heat will be produced. So a higher molecular weight corresponds with higher heat of combustion. Now, this will also be affected somewhat by our branching. So when we have a more branched alkane, so again, if we compare our linear butane versus our branched methylpropane, the branches actually increase the stability of our molecule somewhat. So a more compact alkane molecule actually has more interactions within our molecule. We call these intramolecular interactions, and this creates a more stable molecule overall. Again, remember from our reactivity lectures, that a more stable molecule is less reactive. And less reactivity means it's less likely to combust and will have a lower heat of combustion. So more branching leads to a lower heat of combustion. And again, that's based on the slightly increased stability of our branched alkane. Now, combustion is actually a reaction that many other organic molecules use along with our alkanes. And so this heat of combustion is actually sometimes used as an indicator of the stability of a molecule. Right? So a molecule that reacts with a very high heat of combustion can be said to be unstable. Right? Unstable means more reactive, more likely to combust. A molecule that's relatively stable then would have that relatively low heat of combustion. So you can use that combustion actually to look at what the relative stability of a molecule is. So here we've seen how we can determine the key properties of molecules based on their structural features, and then of course we can compare the structures of similar molecules and see how those features might change with small differences in their structure. We'll follow a similar approach as we look at other kinds of organic molecules, and we'll be able to predict their reactivity and predict their key properties based off of what their structure looks like. And again, those properties and that reactivity are key for determining how we can use a molecule. Right? We need to know if it's going to be reactive and be a poison for us, or if it's going to be reactive and going to be able to be used as a fuel for us.